Hi everyone. This is a kind of a summary of everything we've done in our pressure unit and as it relates to what we did in class. This is a wonderful simulation that you've seen in class many times if you've been here. And right now we're going to start out, we started out our unit by rolling that little ball bearing into the cup and watching it move and establishing that anything moving when it strikes something makes a pressure, which is just a pushing force. Right now, we have absolutely no pressure in this whole system, either outside or inside, because there's no atoms. The minute that we have an atom, and there's just one, now we have a pressure, and that pressure gets every time it hits the side of the container, it makes a pressure, just like our ball bearing made a pressure when it hit that little cup. So without mass, we have no pressure. And what we found out is a number of ways that once we have pressure that we can alter this pressure. Now, one other thing we found out when we mixed the food coloring with the water is that we can make the speed of these atoms change. And remember, since pressure is made every time this atom hits the side of the container, we can have it make more hits if we make the volume of this much smaller. Now this makes the pressure go up because we're getting more hits per second on the side of the container. This is what we did when we did boxes, where we put the ping pong ball in the small box and it rattled around like crazy because of all the hits it was making on the side, versus the larger box where it was really hard to get a lot of hits on the container because the molecules, or in that case the ping pong ball, had to travel so far before it hit a side. So the size of the container is going to make a big difference on how many times this gets hit. Now, when we did boxes too, we changed up what we were looking at a little bit. We found another way to get the size of the containers hit more often, and that was simply to stick in more mass. If we stick in a lot of mass, there's a lot more striking of the insides of that container. More striking leads to higher pressure, and you can see that right over here. As we add this mass, the pressure goes up. In our vacuum chamber, the reason we lowered the pressure is because we start with a certain amount of air, and our vacuum chamber actually draws the mass out. And as we draw mass out, we lower the pressure because we lower the number of hits that are in the container, which allows us to lower the pressure inside that container. Now, unlike this, in our vacuum chamber, we had a huge amount of pressure from the regular air outside here, and right now this is showing a vacuum. So it is not a perfect representation of our vacuum chamber, mostly because the pressure is still higher inside than outside, which was the opposite of the case when we did that. So there we have our two ways right now that we altered pressure. In the boxes, we went small box. We got a lot more pressure because we got a lot more hits. In the large box, we got less pressure because we got a lot fewer hits. And those were the two things that we did in boxes. Now, another one that we can do, and this goes to what we saw when we did, let me add a little more mass just so our pressure reads a little bit more. We saw that when we did the food coloring in the water, the cold water, it mixed in slower because the molecules are moving slower. So we can also change the amount of hits, even if we leave the volume the same and the mass the same. If we cool this off and slow these atoms down, there's less hits. And so we get lower pressure with colder material. Conversely, if I heat it up, now all of a sudden they start going crazy and they start moving a lot faster, and you can see what's happening to the pressure here as we speed it up. Again, we're getting more pressure because we're getting more strikes on the inside of the container. And just to show you, this does a wonderful job. If we build our pressure up a huge amount, the pressure is getting so great that the container can't even hold it anymore, and boom, we have an explosion, off goes our lid, and now we have the cardinal rule of air pressure, which is the high pressure inside is flowing to the low pressure or no pressure outside, which is our cardinal rule of how gas always behaves. It hates to be different. So when you have two pressure areas, a high pressure and a low pressure, then you're going to have one pressure trying to move to another. Now let me reset this, and let's apply this to our syringe. In our syringe, when we pulled the piston back, and here's where this will not perfectly show this, you have to think of the outside here being identical to the inside. So the outside of the containers getting hit just as much as the inside of the container, so our pressures are now equal, outside and inside, and there's not going to be any movement at all. I wish I could show the pressure outside, but it's going to continue to show a vacuum there. When we push the syringe in and we have our finger over the tip of it, we're basically pushing the air inside the syringe into a smaller space. And notice what the pressure does. When the pressure goes up, it's now higher than the pressure out here, and it wants to get there. And it actually, when we let go of the syringe with our hand, it's these inside molecules that push the syringe back to its original position until the inside hits are the same as the outside hits. Now gets where this model breaks down a little bit, and again, it's because we can't show the outside pressure here being the same as the inside pressure. So now you have to do that in your mind's eye. You have to picture a bunch of stuff out here hitting the outsides of the container the same as the ones inside the container are. When we pull the syringe back, we put that air into a bigger volume and the pressure goes down. Since we lowered the pressure here, the outside pressure is still the same as it was before, and it is now the high pressure. It wants in here. And the only way it can get in there is by pushing on the syringe back to where it was until it equalizes. So when the syringe is pushed in, we raise the pressure inside the syringe, and that high pressure pushes the syringe back out as it flows to the low pressure outside. If we make the syringe bigger, we've now lowered the pressure inside. The outside pressure is now higher, and the outside air pushes the syringe back as high pressure flows to low until the pressures are again equal. Anyway, this does a marvelous job of our 3 ways of altering air pressure. Let's recap them one last time. I'll reset it. One way to change pressure is by adding and taking away mass. The more of these we put in, the more pressure we're going to get, because the more the sides of the container get hit. If we want to reduce the pressure, we can take some out. A second way we can change pressure is we can change the volume that they're in. If I reduce the volume, the pressure goes up because I'm getting more hits. If I increase the volume, then the pressure goes down because I'm getting less hits on there. And then the final one, if I don't change the volume or the mass at all, I can change the pressure by slowing these down, resulting in less hits on the side of the container, or I can heat it up, resulting in more hits to the side of the container. And again, just for fun, if I make this high enough pressure, the container can no longer hold it. And when the container no longer hold it, we get an explosion. That was very common in early steam engines. And that's it for our review on pressure.